Okay, good morning, everyone. It's time to start our second day, and we're happy to have the second lecture by Yuji Tachikawa.
Thank you. Thank you for coming back, and good morning. So yesterday, we discussed the anomaly of 2D chiral fermions and its relation to the 3D Chern-Simons terms and to the integral quantum Hall effect system. So that's almost the simplest possible systems with anomalies you learn in high-energy physics side. But today, I'd like to talk about the systems which is even simpler, right? Even simpler than 2D chiral fermions. So let us first remind ourselves what is an anomaly. Usually, in the standard high-energy physics textbooks, anomaly is said to be a subtle phase ambiguity or gauge non-invariance of the path integral measure, right? Which should be an honest symmetry, which is an honest symmetry in the classical action. So that's one way to phrase it. But today, in this lecture series, I'd like to state it in a slightly different way, which applies to the system I'm going to discuss today, which is simpler than the fermions, which doesn't even involve any path integral or anything at all, right? So anomaly is the following phenomenon. A system can couple to a background gauge field for symmetry G, but the partition function Z has a phase ambiguity. Which is not just a random ambiguity, but which is controllable. Right? And this is controlled by a very simple theory in one higher dimensions. So by stating the effect of the anomaly this way, you don't refer to quantization, you don't refer to path integrals. So this applies to more general systems than it is usually done. For example, another thing I'm doing in the last few years is the study of non-Lagrangian theories, non-Lagrangian supersymmetric theories in various dimensions, and study of anomalies for those systems is an important aspect of the works. But these theories don't have Lagrangians, so you first need to make sense of what the anomalies of those non-Lagrangian systems are. And this is the definition which applies in those cases too. So what kind of this system you can consider as the simplest possible quantum field theoretical example? So, well, if you remove even the time direction, things become a bit confusing. So let's keep the time direction, but let's remove all of the spatial direction. So let's consider 0 plus 1 dimensional QFT, which is, in other words, just a quantum mechanics, right? You just have time direction and the Hamiltonian associated with that. And let's say you have G symmetry, right? So G acts on the Hilbert space.
Yuji, you have to write a little bigger, I'm afraid. Please write bigger, please.
Bigger, I see. Okay. So 0 plus 1 DQFT, and which is quantum mechanics, and G symmetric, and G acts on the Hilbert space. And to see the anomaly, you can first start with the simple case of H being a finite dimensional. Well, this is a simplifying assumption. And let's say that the Hamiltonian is 0. Again, this is also to simplify things. There are not many systems simpler than that, right? But still, you can have an anomaly in this system. So now we are going back from QFT to quantum mechanics. And in some of the careful quantum mechanics textbooks, the following statements can be found. So let's say you have a state in the Hilbert space of a quantum mechanical system, and you consider the same vector, but multiplied by a phase. And the standard rule of the quantum mechanics says that the state vector v and state vector cv are in fact the same thing, right? If you take the expectation value, this c is multiplied by its complex conjugate, so it disappears. Therefore, in this quantum mechanical setting, if you allow these degrees of freedom, G symmetry can act on the Hilbert space in the following way. So let's say that each element in the group, for simplicity, let's say that this symmetry G is itself a finite group, right? So let's try to get to the bottom of the story to consider the simplest possible systems. So each G is represented by a linear map from H to H, right? And you would like to have this symmetry action to act consistently on H. So in the usual representation, you require this relation, but because a pure phase doesn't affect the physical state, let's allow some phase factor, right? So this is something called the projective representations, and C, G, comma, H is the projective phase. But let's think what happens to the partition function if the symmetry is projected. So let's say this is the time thermal circle, S1, right? So the partition function Z is trace of exponential minus beta h. But we are taking a very simplifying assumption that this is just 1, so you don't even have to consider it. And let's say we insert the transformation GH. So what this means that when you go around the circle, you get the system is affected by this element GH. So you insert GH, right? But you can represent the same background as doing G and H separately, right? And if you write this down, you instead get rho G times rho H. They are the same when the representation is a genuine representation, but they are different if the representation is projective. So you can easily see that this is, in fact, the lower expression times C G comma H. So this way, you really have a system which can couple to background G gauge field, right? And it produces some phase ambiguity, which is controlled by this factor. So this is the simplest possible system, anomalous system you can think of. No quantization involved. It's just a finite dimensional vector space. So let's study it in a bit more detail. Right. So first thing is that you cannot use arbitrary set of numbers, C, G, H. There's a certain restriction on the allowed choice. So let's see how it arises. So to see that, you compute rho GHK in two different ways. So this can be computed as rho GH, rho K, which is C GHK, which can further be decomposed as rho G, rho H, rho K. And you use the rule here, CGH times CGH times K, right? But you can rewrite this expression in the different order by first splitting into G and HK. So this involves a factor G comma HK. And you further decompose rho HK into rho H and rho K. Rho HK, right? So this part and that last part is equal, but the phase you obtained are not, directly the same, right? Did I forget something? You're right. Thank you. So these two expressions should be the same. So one condition is that these two expressions are the same. Right? So this is one condition. But this is not the whole story, because if we are given a set of matrices, rho of G, you can redefine them by multiplying by phases depending on G, right? This rewriting changes C in the following way, as you can easily check. That this is given by CGH times BGH over BH BG. So when you discuss the projective phase, you need to identify two different looking projective phases related by this transformation. This means that the set of projective phases distinct projective phases is given by, let's say this is relation sharp, and this is the expression flat, and distinct projective phases is that CGH satisfying sharp divided by CGH of the form flat. And this object is known mathematically as the second cohomology group of finite group G, whose value is in U1. This is really the definition of this group. And let me explain why this is denoted in this way by explaining you a general situation. So I'm not perfectly used to this German way of erasing the blackboards. But, right, so let me define HD, G, A in general. Here, A is something which G acts on. And to define it, you first define C, D, GA to be the set of functions from GD to A without any linearity or anything. And then you define the differential D, which is CD to CD plus 1 in the following way. So let's say you take an element F from here, right? Then we would like to define element DF there. DF take D plus 1 elements, right? So G1, G2, to D plus 1. And this is defined in the following funny way. So the first term is that G1 acts on F, G2, to G, D plus 1, right? I mean, F is an element of A, and we have an assumption that G acts on A, so G1 can act on the value of F. And then you have minus F, G1, G2, comma, G3, to G, D plus 1. And then I'd like to keep this expression above. And let me erase this part too. And then it continues. Next term is plus F, G1, comma, G2, G3, G4, to GD plus 1. And then you have F, G1, G2, G3, G4, So you now get the idea. And the final term is minus 1 to D plus 1, F, G1, to GD. So this is the definition of the operation D. It looks a bit complicated, but you can check that D squares to 0. So it defines a cohomology. This one. In fact, that's the second to the last term, and you also need this term. So I thought so. Yeah, I think so. That's the second to, yeah. At this point, you have G1, G2, to GD, GD plus 1. So there's a corresponding object here, right? G1 is outside of the paren, if I remember correctly. So let's check that this is it. So thank you for pointing that out. So this expression is in fact supposed to be DC is 1, while this is dB. There's a bit of a comment before trying to check that. This expression of D is written in the notation where the group operation in A is written additively, right? But U1 is usually written multiplicatively. Therefore, instead of plus and minuses, we have plus 1 power and minus 1 power, etc. And df equals 0 in the additive notation means d squared equals 1 in the multiplicative notation, because 0 is the 0 element in the additive notation, and 1 is the trivial element in the multiplicative notation. So let's check that this is indeed DC, just for checking the definition. Right. So let's expand this definition when d happens to be 2, right? So the case d equals 2. Then dc g1, g2, g3 is first g1, c, g2, g3. I guess I should use GHK, right, to directly compare. So let's say GHK, and this is CHK. But here I'm using the fact that G acts on U1 trivially. Therefore, this action is trivial, so you can just erase it. So you can forget about it. So that's the first term. The second term is C, GHK inverse, right? And then the next term is C, G, HK. And the last term is, as I said, this one without a K. So you really need this last term to match with this. And you can also check that this B is dB. So that's why we use some cohomological notation to denote this projective phase. So that's my short review on the relation between the group cohomology and projective phase. But let's see. So we now have understood fairly well the simplest possible anomalous systems in the world. But yesterday, I told you that the anomaly of a system can be understood as a variation, boundary variation of the effective action of a system in one higher dimensions. That goes under the name symmetry protected topological phases. So what would be how does this two-dimensional theory looks like? So that's the question. So what we want to consider is a 2D system, 1 plus 1D system with G symmetry. Right? Here, G is a finite group. So the rule is that you have some 2D space, right, with some G bundle, right? And you want to assign some partition function Z 2D to it. So this is what the 2D system with G symmetry should do. And we are assuming that this is just a phase. So that's the important part. Now, in high-energy physics, we often talk about G gauge field for continuous G. How do we imagine, how do we picture G bundle for finite group, right? So the idea is to realize the action of G in terms of a domain wall. So let's say we have a domain wall labeled by G in a 2D space, right? By this, I mean, suppose you are here, right? And you are going to cross the domain wall, and then you are affected by G. So that's what we mean by having a domain wall G, domain wall labeled by G, right? You can have other domain wall labeled by H, right? So that if you cross here, you are affected by the transformation H. And then when the domain wall labeled by G and domain wall labeled by H merges at some point for consistency, the domain wall emerging from this junction point should be labeled by Hg. So that's the structure. So any G bundle can be thought of as a complicated network of domain walls, each segment labeled by G, H, G prime, whatever, right? So one way to assign a partition function to this domain wall systems on 2D world volume is this. So let's say you have a junction of G, H, and forming GH. GH, you assign a phase. So assign a phase C, G of H, GA, comma H. And you just define the partition function to be the product over all junction points and you multiply all these phases. So that's one way to define it. But you need to ask whether this is really OK to do such a definition. So the point is, you want to guarantee that you want it to be gauge invariant. What do we mean by the gauge invariance of this domain wall network system? The point is, a single G gauge background can be expressed in many different ways using domain wall networks. So let me draw a very simple example. Suppose you have 3 walls labeled by G, H, and K. So first forming GH and then GHK. So this represents a certain G bundle, right? But the same G bundle can be represented in a different way by merging in 2 different orders. Right? Sorry, this is the same. I'm so sorry. Right. GHK. Right? So instead of doing the gauge transformation of one form by D something, we regard this change, topological change of the junctions of domain wall networks as the substitute for the gauge transformation. And you want the U1 phase assigned to these 2 subgraphs to be the same. So what would be the phase you assign to this? This is C, G, comma H. And this is C, GH, comma K. And similarly, you have C, G, HK times C, HK. And you would like them to be equal. So this is exactly the same condition you found in the case of projective phase. So this type of 2D system can be defined given any projective phase. So this construction is originally introduced by Digraph and Witten in their paper from 1990. And they used this not as a symmetry-protected topological phases, but rather as the starting point for the study of 2D gauge theory. So here I'm using this action as an effective action of the system responding to the background G bundle. But you can promote this G bundle to be dynamical, and you can perform path integral over it. Right? So, or in other words, you can sum over all possible G bundles. That will give you a 2D gauge theory with gauge group G. But here, let me stress that G here is considered a background flavor symmetry. Right. So now I need to explain to you that this is exactly the 2D theory you need to cancel the anomaly of the 0 plus 1 dimensional system. So let me explain that. This is very simple. So let's say this is the boundary of the 2D system. So this is 1 plus 1D. This is 0 plus 1D. And here you have some Hilbert space associated to this boundary, right? And suppose you do the transformation by rho G and rho H, right? By coupling this two-dimensional system to 0 plus 1D system, such an action of rho G needs to be connected to G domain wall, right? H also needs to be connected by H domain wall. And eventually, they join to form GH, right? But you can perform the combined gauge transformation of this system. So what happens is that you have a boundary, you have the bulk, and you have just one insertion of rho GH, and you have the domain wall labeled by GH, right? So what happens is that on the left-hand side, you have the phase CGH associated to the junction in the bulk. On the right-hand side, you replaced rho G times rho H by rho GH. So there's a factor C GH times rho G times rho H appearing here. Therefore, if you just consider this system, boundary system alone, you have this unwanted phase. If you consider just the bulk system alone with some open boundary, you have this floating CG comma H. But by coupling them, this left-hand side and the right-hand side gives exactly the same number as the outcome. So this shows you that the anomaly carried by the boundary is canceled by the anomalous gauge variation of the bulk 2D system. Very, very simple, right? At the boundary, you just have finite dimensional Hilbert space. In the bulk, there's just one dimensional Hilbert space and just phases. So it's the simplest possible system you can think of. So this is all very general. So let me just give you an example. Let me give you just an example. Let me erase this too. I don't know. This is one way to assign a phase given CGH. There is a general, very general abstract nonsense guaranteeing that this is almost the most general way to assign a phase given a finite group G. Yeah. As I will explain tomorrow, this only captures the, in some sense, pure gauge part of the anomaly. And you need to also include the mixed gauge gravity anomaly kind of object. But once you include those, then this can be shown to be the most general construction. Yeah. So let me give you an example. Unfortunately, the simplest set of finite groups you think, Zn, don't have non-trivial projective representation. This is trivial. Too bad. So the next simplest thing you can consider is to take Z2 times Z2. This is known to be Z2. I'm not going to show that. If you have enough time, you can check that by directly solving the equations, which is not very hard. But let me give you a non-trivial projective representation. So let's say that first G2 is the additive group of 0 and V, so that V plus V is 0. And the second thing is 0 and W, right? Or maybe I should use the multiplicative notation. 1 and V and 1 and W. And I just say rho V is, 1, 1, 1. And the rho W to be, sorry, I'm completely lost. You just take this sigma matrices and, right. Yeah. Which one to take doesn't matter at all. So, rho V squares to 1, rho W squares to 1, which is nice. But rho V, rho W is minus rho W, rho V, right? So this is a projective representation. This is non-trivial. And from this, you can read off the annoying fact that CVW. And then you can construct some 2D theory, right? So let's see what kind of 2D theory you get. So let's say you consider a torus and the following network of defects. This part and this part needs to be identified, and the other part is too. And you just assign VW, forming VW, separate into W and V. So you have two junction points, and you can check that one junction point gives -1 and the other junction point gives +1. So Z2D is -1 in this case. So this means that this means that if you have a torus with non-trivial holonomy around this circle by W, and if you have a non-trivial holonomy around the other circle by V, you get a non-trivial phase -1. So this was originally introduced by Varfa under the name of discrete torsion. In the setup of orbifolding construction of world sheet theories. And later, so this is in 1986, right? And then about 10 years later, in 98, Douglas noticed that if you have D branes in this orbifold with discrete torsion, the D brane, which is a boundary condition for the world sheet theory, needs to carry a projective representation of the orbifolding group G, right? So in the world sheet language, in the technique of perturbative string theory, this was a weird phase. And what Douglas found in the context of D branes was also a strange relationship between the discrete torsion and the projective representation. But it's just a manifestation of the fact that the projective representation carries an anomaly of a finite group, and then you need a bulk symmetry-protected topological phases, which gives you this additional phase, -1. So the relation is exactly the same as the complex fermion and the bulk Chern-Simons term. So it's just another manifestation. Right. So let me give you just a slightly different way of representing this discrete torsion phase, just to prepare for the generalization for tomorrow. So this is one way to represent gauge field, finite gauge field on the 2D surface, but you can represent it using also some cohomology groups. So let's say this is a torus, right? And you can consider an element of H1, T2, taking value in Z2. So I assume that you are familiar with the Doram cohomology groups, but maybe not everybody in the audience is familiar with this Z2 valued cohomology groups. So this is a bit complicated. So let's remind ourselves what cohomology group, Doram cohomology group does, right? So suppose you have a one form, right? And you integrate that over some closed curve. So this gives you some number, which is usually a real number. So this is an element of H1 space-time valued in R. So H1, first cohomology of the space valued in R is something which assigns a real number given a homological cycle. So you define H1 of T squared Z2 to be something which assigns to any one cycle a number in Z2, right? So that's a working definition. So, and here we have two Z2 involved. So let's distinguish them by Z2 associated to V and Z2 associated to W. So let's say this is Z2 associated to V, and then you take a gauge field, background gauge field, say A, associated to this first Z2 factor. And similarly, maybe capital A. I haven't really decided. And similarly, you have H1, T2, Z2 associated to W, and you take another gauge field, capital B. So using that, and then standard operations in Doram cohomology works with these discrete cohomologies. The mathematician will be very angry if I denote the multiplication of two cohomology elements using wedge, but for high-energy physicists, I think using wedge would be more familiar, so let me just use wedge. So this is an element in H2 of T2, Z2, right? So the degrees add up, and then you can integrate this A wedge B. First, you get Z2 cross Z2, but because Z2 is a ring, you can take the multiplication. Yeah, so you get the element in Z2 times Z2. So you can now integrate it, right? So if you integrate degree 2 thing over two-dimensional manifolds, in the case of Doram cohomology, you get the number. So here you get the number in Z2, which I take to be 0 and 1. Right? So you can raise it exponential pi I T2 A wedge B, and this reproduces this number. So this is a general way to write down this discrete torsion phase, and by using this notation, you can use whatever two-dimensional manifold. Right. So this might be a bit more, this might look a bit more familiar to many of you compared to this completely combinatorial expression. So this looks like taking two gauge field, multiplying them, integrating, and raising to the exponential. Now, I reviewed the case where G is an internal symmetry. So let's move on to the case where G is a space-time symmetry. Right? So I guess it's better to scrape off the waters.
Yuji,
Yes.
could you say a word about continuous symmetries? So far, you're looking at discrete symmetries.
I'm just looking at finite group symmetries, yes.
But in principle, there could also be projective representations for continuous symmetry. But
yes.
Can it just be reduced to the center of the group?
That's right. In fact, if I have time, I will come back to the case of U1 at the end. Thank you for pointing that out. So let's consider G to be a space-time symmetry. Right? In 0 plus 1D system. Right? You just have time direction. What kind of space-time symmetry can you have? There's only one thing, which is time reversal, because there's only a time, which is a Z2 operation, right? But this Z2 operation is a bit different from the Z2 operation we have been seeing so far, because as you learn in quantum mechanics textbooks, time reversal T is an anti-unitary operation. So rho T or rho of T is an anti-unitary operation, right? This can be phrased in the following way. I mean, rho T, if acted on after a complex number, this gets changed to a complex conjugate, right? So this is why I defined for you a very general cohomology group, HDGA, where G acts on A non-trivially. Here, A is U1, which is a phase, but Z2, which is a time reversal symmetry, acts on C via complex conjugation. So that gives you some additional thing in the analysis of the projective representation, but everything goes through. But in this particular case, the analysis of the projective representation is very simple. You don't have to go through all this group cohomology business. You can just directly find them out. So let's do that. It's a fun computation, right? In any case, there are only two elements. One, identity element, and T, the time reversal. One is mapped to the identity matrix. T is mapped to rho T, right? Now you allow projective phase. The only projective phase you can think of is that rho T squared needs to be equal to 1 up to a phase. So this is some phase alpha. What kind of alpha is allowed? This is a fun computation. So the thing to do is to decompose rho T cubed in two different ways. If you view this as rho T squared times rho T, this is alpha times rho T, right? On the other hand, if you think of this as rho T times rho T squared, this is rho T alpha. And I just draw here that when a complex number passes through rho of T, it gets complex conjugate. Therefore, in order for this and that to be equal, alpha needs to be its complex conjugate. But because alpha is U1, this means alpha is plus minus 1. So this means that there can be two different types of representation. One is a genuine representation. The other is a projective representation. Now, you wonder what is the corresponding bulk to the system. So before going further, let's keep it on the blackboard that there are two versions. Right? So this is the trivial phase. This is the non-trivial phase. What happens in that? What's the corresponding 1 plus 1D thing? 1 to 1D QFT? Right? So you need to give so in the case of internal symmetry, we considered two-dimensional manifold together with finite group gauge field. Here, we need to consider some non-trivial thing involving time reversal, right? We are considering relativistic theory, so time reversal in 1 plus 1D is basically the same as parity reversal. So this means that in 1 plus 1D, corresponding 1 plus 1D QFT can be formulated on a non-oriented manifold, such as RP2 or Klein bottles, right? So you want to assign some phase to these non-oriented manifold. So you assign some phase Z to D. So everybody knows that oriented 2D manifolds are distinguished by the number of holes, right? In the case of unoriented manifolds, it is known that any unoriented manifolds can be written as ordinary 2D surface with a number of cross caps inserted, but with the condition that two cross caps can be traded with one hole. So that's the rule. So one way to assign a phase in a non-trivial way is to raise the number of cross caps to -1. So this is a non-trivial two-dimensional QFT, which is very simple. Again, you always have one-dimensional Hilbert space, and the partition function is always just a phase. That's it. And if I had time, I could have explained to you that this particular bulk theory correctly cancels the anomaly associated to this this phase, but let me skip that. But let me mention just one thing. So you see, when rho t squared is 1, and let's say you have some additional symmetry G acting on the Hilbert space. You want this G to commute with the time reversal rho t, right? What does it mean? This means that, anti-unitary operation squaring to 1 determines a real structure on H. Therefore, when G commute with rho t, this means that G is a subgroup of O n, where n is the dimension of H. On the other hand, if rho t squares to minus 1, rho t effectively behaves as J of quaternion. Therefore, when G commutes with rho of t, this means that G is a subgroup of SP 2n, where 2n is the dimension of H, right? So if you accept the fact that this phase cancels the anomaly, you now see a correlation between a certain subtle phase associated with a cross-gap and the fact that symmetry of the boundary theory is ON or SP2n. This is known in the, this has been known in the string theory community for such a long time. I think the first appearance of that computation is really the classic paper by Green and Schwartz of the anomaly cancellations of type 1 theory. So there, he computed the anomaly cancellation of the world sheet theory by summing over the contribution from the torus, Klein bottles, and Möbius strip. And they noticed that depending on whether you take the Chern-Payton factor of the world sheet to be SO or SP, you need to assign a subtle phase, subtle minus 1, in the case of the Möbius strip amplitude. And therefore, in order to correctly cancel the tadpoles, you need to choose one choice. And that happened to be SO32, but that's another story. But the important point here is that this somewhat mysterious relation between Chern-Payton index being ON or SPN and the fact that you can introduce this additional phase inside the world sheet bulk theory is just a manifestation of the simple fact that the time reversal Z2 symmetry on the boundary can have an anomaly, which is then canceled by this non-trivial phase theory in the bulk. So that's another manifestation. And in the remaining 2 minutes, let me just briefly mention the case of continuous symmetry. Right. So let's consider the case when G is U1. Right? This time, let's start from the 2D theory. 2D trivial theory has an action which is a pure phase. What kind of action you'd like to consider? Well, the thing I'd like to consider is just this one. So you integrate the U1 gauge field over the 2-dimensional space-time, and you multiply by theta. So this is just a 2-dimensional theta angle. And I emphasize again that I'm using this F as a background field. Right? So this is gauge invariant and nice. What happens if this is formulated on a space-time with boundary? So you have M, and this is the boundary. So what happens is that you can partially integrate F over M as, this is dA, right? So A integrated over the boundary with the coefficient theta. This means that boundary behaves as if it has charge theta, right? But this is weird. Theta is a variable. Theta over 2 pi. I think I forgot to put the factor 2 pi here. Anyway. Remember, theta is a variable periodic in 2 pi. So if you use general theta, this charge is not integral, right? But here we are being careful about the periodicity of the groups. So if I say a representation of U1, the charge has to be an integer. But this boundary has non-integral charge. In other words, this is a projective representation of U1. This is a projective of U1. So it's the same story. In this case, this fact was pointed out by Coleman in his paper Massive Schrödinger Models, and it's from the 70s. So my lecture is going back in time in some sense, getting easier and easier as the lectures proceeds. And let me finish by remarking just one comment. So you might still think that this bulk theory is a bit too trivial, right? A bit too trivial. But you can, in fact, perform dimensional reduction of the bulk theory. You see, yesterday we started talking about considering 2D chiral complex fermions compactified on S1 with a certain holonomy, theta, which is given by the integral of A along the x direction. And later in the lecture, I said that it's better to think of it as a boundary of a 3D system with the action 4 pi I A dA, right? Let me just write AF. Now you can reduce this system along the S1 direction. If you reduce this system along the S1 direction, you have just one-dimensional boundary reduced along X, right? And now you have two-dimensional bulk. You reduce this action along the X direction. So this A is replaced by theta. And you need to remember that A is hidden inside F2. So you get a factor of 2. So the bulk theory has, in fact, the effective action 2 pi, I theta over 2 pi times F. This is exactly the bulk system I just considered. Therefore, this means that the boundary system should have charge theta over 2 pi, right? And this is exactly what we found if we compactify 2D chiral complex fermion on a circle with a holonomy given by this theta. So this is another derivation of the fact that the vacuum of a complex chiral fermion on S1 with this holonomy should have this fractional charge. So that's how to relate today's discussion with yesterday's discussion. So this is the end of my talk today. Thank you very much.
We have time for a few questions. Yes, please.
So you have described an anomaly inflow mechanism where you start from quantum mechanics. Then you can add a 2D bulk theory to cancel the anomaly.
Right.
So it seems that possibly this extension may depend on the choice of Riemann surface or 2D manifold that you pick to extend your quantum mechanics, possibly also on the G bundle over it. So can you comment on the dependence on if there is a choice?
Thank you for the question. I wasn't very clear about the independence toward how to do the extension. So let me repeat the discussion of the cancellation of the projective phase by the bulk vertex. So to do that, the important point is the following. In fact, it's independent. So we are imagining to have a one-dimensional boundary, right? And we are considering a certain configuration where you have insertion of rho g and rho h, right? But it's perfectly OK to have lots of other insertions of the group transformations on the boundary. Similarly, when you extend it, you can have as many holes as you want, and you can have very complicated domain wall networks representing whatever G bundle you can think of. But the important thing is that once you say that there's this insertion of rho of G and rho of H, there's a tiny bit of region here, with domain wall labeled by G attached to this rho of G, and domain wall labeled by H attached to this insertion of rho of H, right? This is having these two walls is forced by the condition that you are going to insert rho of G and rho of H at the boundary, right? And we can repeat the same discussion I did during the lecture, just looking at this very small patch. So you just replace this patch by keeping the entire rest, which can be however complicated. You can just replace this local patch to this form. Right? Then there are lots of complicated phase factors associated to C here. There are lots of things going on around there. But the important point is that the change in the projective phase coming from fusing rho of G and rho of H into rho of GH is canceled by this additional vertex here. So this is a very local operation and guarantees that it doesn't depend on the extension or the choice of the 2D manifold.
Sorry, I was asking about the dependence on the full partition function on your complete extension. Because you can do several extensions with different 2D. You see, when you define the partition function, you multiply by the full 2D partition function, if you wish.
Right.
So there is a choice here of which complete extension you do, and I was asking about the dependence of the partition function on this extension.
But that does depend on the choice. But that's perfectly OK. I mean, in the extreme case is where you just don't have any boundary, right? In that case, choosing a bulk manifold is really choosing a bulk manifold, and choosing a bundle on it is choosing a bundle on it, and the partition function associated to that is some number depending on that. So the point is that once you put this boundary, the bulk, we are taking this condensed matter physicist point of view seriously by considering the whole system to be the physical system. So you just want to assign a unique partition function to the whole system. Yeah.
Okay, any other brief question? So, if not, let's thank you. Is there one? Yeah.
Sorry.
Yeah, please.
Just a simple question. So in the case where the 2D surface is oriented, I guess you don't really mind whether the discrete group is abelian or not, because you have a consistent way of knowing how two domain walls join. And,
that's right.
In the case of non-orientable surface, yeah.
So you want to extend the discussion to the non-orientable case?
Yeah.
So that's a very good question. In fact, in order to properly extend the discussion, you need to specify what happens. So here, in the first part of the talk, I was mainly discussing domain walls labeled by G, right? And then I discussed a case where T rho t is anti-unitary, right? I didn't have the time to discuss how this bulk theory, which assigns -1 to the power, which is the number of cross-caps, cancels the anomaly of rho of t. But the important point is that you need to introduce into the bulk a new type of domain wall, which reverses the orientation. So you need to consider it as a new type of orientation. And then you need to decide what happens if an orientation reversing domain wall intersects with this internal symmetry wall, G. So in that case, there are many choices. This G can be transformed into another group element, for example, and you can also assign some phase right here. So there are many things involved, but you can carry it out the analysis and properly extend the analysis. Yeah.
Okay, so in view of time, let's postpone any further discussion to the afternoon, and thank you, Yuji, again.
Thank you very much.